Okay, so let me explain what this graph is. And this is one that we briefly talked about at the beginning, but now we're going to spend more time talking about it. So let's say that I want to do a simple example of hydrogen and oxygen to make water. Okay? So here I've got some oxygen molecules and some hydrogens. It's correct, they're diatomic, all this good stuff. So let's say that I want to make water. So I've got oxygen, I've got hydrogen. Now, you all have seen a hydrogen balloon explode. What do you have to do? Fire. Okay, you have to have some activation energy, right? So if you think about it, if you're going to take 2H2 plus O2 to make 2 waters. Okay, so if you think about the mechanism that has to happen. So here's my 2 hydrogen. I'll drop my hydrogen. Here's my, it's so light. So here's the hydrogen, okay? And then here's my oxygen. So on these transition states, what I've got to do is that if you think about it, I've got to break the bonds that hold the hydrogen together. So now I've got that, and I've got this, okay? And then I've got that, okay? So at that brief moment of time where those atoms have been broken apart, because I can't make water if my oxygen is stuck together, okay? I can't make water if my hydrogen remains stuck together. I have to break those bonds. So in that short amount of time where those hydrogen and oxygens were existing as individual atoms, that's that transition state. That's what's happening when we introduce the fire. So that fire is going to initially break some bonds that hold the hydrogen and the oxygen together. So now, I've got this in this transition state. So what's happening from an energy standpoint, I put energy into it, okay? That's that activation energy. Now, it's cool because I have to have some amount of energy, which would be bad, because if not, like I've got a tank of hydrogen back there in my room, in the back room. If all I had to do was just introduce hydrogen into the room and it would immediately begin to react with oxygen in an explosive manner, that would be bad, okay? It was like, what happened in the back? I don't know, somebody opened up the valve, boom, okay? Bad. So there has to be some amount of activation energy. You all have done that. You all have lit Bunsen burners, right? Oh, Bunsen burners. What do you have to do? Strike it up, right? You have to have a striker. Thankfully, it's like, oh, you want the Bunsen burner to light? Oh, just turn it on. That's all you have to do, okay? That would be bad. So it's okay that we have to have some activation energy. It's not, it isn't like, oh, we just have to mix it together and the reaction starts. No. So at this point, I'm at the top of the curve. You can think of this in terms of like a roller coaster. So at this point, we're at the top of the roller coaster, okay? Woo, everybody's ready to go. Everybody's excited. Woo, here we go, right? So then, whoa, you go down the roller coaster. So the oxygen bonds with the hydrogen, and we get Mickey Mouse, okay? So we went from separate molecules into water. In this situation, the products, in this case of water, and there's the reactants, hydrogen and oxygen, okay? I end up with less energy. And I know that because when I light off a hydrogen balloon, there's fire, there's heat. So the fire and heat that's given off of that reaction, if you go with the roller coaster analogy, that's like the people going, wah! Okay, and they yell and scream and they wave their hands as they go down the roller coaster. So people going, wah! On the roller coaster, that's the energy that's being given off in the formation of the bonds. okay? Now, in this situation, the products have less energy than the reactants. If that happens, this is what we call an exothermic reaction. Energy is being given off, okay? Your body runs on exothermic reactions, okay? That's why you all give off thermal energy, okay? Your little furnaces. So on a cellular level, you are burning energy and it's exothermic reactions, and you're giving off that energy, okay? If you were endothermic reactions, that means you would draw energy in from the surroundings, okay, which would be really weird. So if you're on an endothermic reaction, you end up here, okay? In that situation, and these are pretty rare, and later on you'll see why these don't happen as very often. Because Mother Nature, this will make sense later on once we get into more of a philosophical discussion, but Mother Nature likes a hot mess, okay? So Mother Nature likes exothermic reactions that create disorder. That's what Mother Nature really likes. Mother Nature likes a hot mess, okay? She doesn't like a cold, clean room. She wants a hot mess, okay? Which is why my room looks like what it does, okay? So it's all, the disorder in my room is all part of a larger display of science, philosophy. How about that? Okay, so now, but here's the deal though. What if you reverse this? What if I have water and I want to turn it back into hydrogen and oxygen? Now, you all have done this. What did you have to do?
Electrolysis.
Electrolysis. You had to dump energy into it. You hooked it up to the battery, right? Because hydrogen and oxygen don't spontaneously form from water. If it did, we wouldn't have oceans. If hydrogen and oxygen would spontaneously change, or if water would spontaneously decompose into hydrogen and oxygen, we would not be here having this discussion, okay? Water is stable. So if you reverse the process, then, let me kind of draw this so it's a little bit less crowded, okay? So let's say here's your hydrogen and oxygen. Going in this direction, that's your activation energy. And this right here, from that initial baseline, is your change in energy. And there's your water. My change in energy is less. It's an exothermic reaction. Woo! Big bang, right? Cool. If I want to start with water and end up with hydrogen and oxygen, then here's what changes. This now becomes your activation energy. So it's like a roller coaster. Now I have to push that thing all the way back up to the top of the roller coaster. That's a huge input of energy. But then, if I reverse it, then my delta E, okay, my change in energy, is a positive number. So this is why people talk about, oh, let's use hydrogen gas as a fuel source. Great. It's fantastic. All you have to have is water. You split it up. You split the hydrogen from the oxygen in the water. But what do you have to do that? Put energy into it, okay? So to get the hydrogen off the water, that requires an input of energy. That becomes the debate. Where do you get the energy? Now, we'll talk more about this later. But another potential source of a lot of hydrogen is methane, okay? Because methane is CH4, okay? So, like landfills, for example, when they decompose, they give off a lot of methane. Feedlots, when you feed a lot of cattle or dairies, they give off a lot of methane, okay? It's cow poop, okay? Gives off a lot of methane. Another reason I don't like biology. But so one option, and there's actually a company in Japan that's taking manure from a dairy, siphoning off the methane, stripping off the hydrogen, and using the hydrogen in fuel cells to produce the electricity to run the dairy. But the cool thing about using hydrogen and oxygen is what's your only byproduct?
Water.
water. Okay, so that's the cool thing. So if you can find an energy convenient way to strip off the hydrogen, whether it's methane, water, whatever it is, and that doesn't require a huge input of energy, that's not bad. Okay, now, there's your challenge. Now, let's talk about catalyzed reactions. So if something is a catalyzed reaction, okay, listen to me very carefully. So on a catalyzed reaction, let me go back to that diagram. So here's hydrogen and oxygen. And let's say this is the initial reaction. There's my delta E. And this is my activation energy. So let's say that's the normal reaction. So what a catalyst does, listen to me very carefully, what a catalyst does and what a catalyst doesn't do. What a catalyst does is that it lowers the activation energy, okay? But the overall change in energy remains the same. So catalysts don't change whether it's an endothermic or exothermic reaction. What a catalyzed reaction does, and this is with a catalyst, is that it lowers the hill, okay? So it makes it easier to start the reaction. If you go with like the second graders and the bar, so this would be the normal bar, okay? Only a certain number of kids can jump over the bar. On a catalyzed reaction, we're going to lower the bar. That makes it easier and more available for kids to jump over the bar. Okay, more kids can jump over. So your cars, if they're a gasoline engine, have a catalytic converter underneath them. It's a catalytic converter. Imply that it is a catalyst, okay? So it reduces the activation energy for the production of like nitrogen monoxide. I can't remember exactly what it does. But it acts to lower the activation energy so that you can reduce the pollutants coming out of the car. So underneath your car, you have a catalytic converter. It's a catalyst.
People steal them.
Yeah, and then people steal it, which if you ever, anyway, don't even get me started. I'll say bad words. Oh,
Did
yeah.
somebody steal your catalyst?
No, I'm just saying,
in
people that
general?
steal, I have,
okay.
I'm sorry, I
I
have
sympathy for
absolutely no tolerance whatsoever. None, zero, zip.
Zilch, perhaps?
The stealing.
I'm just kidding.
I see the direct comments policy, okay.
Yes.
I was just
exactly.
testing to see how far you were on that. That's crazy.
All right,
Very
hold on. Now, we're gonna make it a little bit more complicated.
This is
You missed the best thing when him and Charles were just laughing at each other.
yo, he was there for
What are you doing?
What?
Or are you just like,
They're talking
Lean
about
back.
stretching my pecs. I'm not even gonna go. That's all. Yeah, that's on video. That's,
people are
that is on.
watch this lecture, it is really bad.
That is documented. Right
That's
there.
probably valid.
We need to make like a compilation of all the best.
And
I'm
put
just
it on a
stretching my
t-shirt.
pecs.
Yeah, because they're all on video, because you record all of these.
Not all.
Most of them.
Only when
It's
we
like
start.
it's
Who's gonna
extra
go back
filming
and
every
watch all
one.
the videos and find all the
When I-
quotes
Cohen 100% will.
and combine
You
them?
do
You
that.
can't, there's too many.
Yeah.
I'll get my,
Too many
like, my
now.
video editing skills from
You
my
told me this have to
YouTube
do
channel
something.
days.
Hey, I'd rather watch the videos.
We would do it in
It's a time limit.
A lot
It's
of,
gonna be like.
and a lot of time spent thinking about like chemistry and physics, which I don't
Or maybe not, I don't
Because if you look at
That's fine.
I almost had no.
It means I can also see if my answers are correct. My bad.
Because then if I'm not here, I have to go watch
I
them.
meant just put
and
down
then-
right answer.
Okay, now, this one's gonna be more complicated. So this is where,
This one.
this one. So this is where we're gonna pull what we talked about with like rate determining steps, okay? So this one has two different activation energies. So your first activation energy, you're gonna start at A, and those relative maximums, if you're a math nerd, are the transition states. That's where you separate the particles. So what's gonna happen is that you're gonna take A, and then you're gonna form a product B, and then B is gonna get consumed, and we're gonna end up making C. So A is gonna turn into B is gonna turn into C. So A is gonna turn into B is gonna turn into C. Now, based upon the activation energies, what's the slow step? A to B or B to C?
A to B.
Why is that the slow step?
Takes more.
Requires more energy, right? That's the higher bar. So A to B would be the
Rate
slow
determining.
step.
Can't put it into words. He's
Okay?
about to connect all the concepts together.
Huh?
He's about to connect all the concepts.
Well, quite a few of them, yeah. Now,
Maybe not all.
so B is an intermediate because of the fact that we're going to make B, but then we're going to
Get rid of it.
get rid of it. So B to C has the lowest activation energy. So that requires the smallest amount of energy. So B to C is going to be the fastest step. Is the overall reaction endothermic or exothermic?
Exothermic.
Exothermic. Why?
Because it
So
goes
you
from a
have-
Yes,
high.
overall you end up with less energy than where you started. Okay? So let's just make up numbers. Let's say this is 15, and let's say that's 45, and let's say that's 30, and let's say this is 5. Okay? Usually this is going to be kilojoules, but let's just, for the sake of argument, have numbers. So, what's your activation energy on the A to B reaction?
30.
30, because I'm starting at 15, I end up at 45, so my activation energy would be 30. Okay? On the formation of B, that drops back down to 30. So, overall, on my reaction from A to make B, is that an endothermic or exothermic reaction? Just in the production of B. That's endothermic. That's going to take energy in, right? But then I can take B and change that into C. So overall, from the entire reaction, that's a 5 over there on the end. So overall, what from the entire reaction, what's my change in energy?
Negative 10.
Negative 10. Because I'm starting at 15, I'm going to end up at 5. My overall delta E is going to be negative 10. Got that idea? Cool. Okay. So let me see. Got done with that. Got done with that. Cool. We're good. Got that one. Okay, now some random equations. On these random equations that I'm going to give you, no, they're important, but they're not on your equation sheet. So what I'm telling you is that don't memorize these. I will always give them to you on the test.
We'll look at the exam. Give these to us.
They're just going to ask you about the concept. I want you to be able to actually do the math. Okay? All right. Not a problem.
I'll get to the exam.
Don't.
LOL. What a freak.
That doesn't look like an equation.
Looks like another.
I fear that might
It's
be a
another
graph.
graph.
No.
So you lied to us.
What did I say?
You're gonna send us a bunch of equations.
Oh, but this is going to come from this.
Lie.
I already titled my page random equations. I can't put a graph on here.
And graph. Do it in like parentheses.
I knew it, but that was like a good thing too.
We're going to start with what you know.
I don't know what anything.
This is the reaction you already know.
It doesn't look like it.
I don't know what that is.
You just did a graph on this.
Wrong.
That doesn't mean I know it.
Pretty sure I have this one written down. Look at that, I do.
Oh, yeah, I do too.
Frequency
It's somewhere
factor?
probably.
It's now.
You're gonna explain it later.
Sounds like.
Frequency.
It's just the y-intercept.
Oh.
Fre-
1/10.
Frequently.
Okay.
Oh, never mind, that's
Kelvin and Celsius.
So,
Good
all
job.
this is a graph that you all have already drawn. You have the natural log of K on 1, you have the inverse of temperature in, what units, Bethany?
Kelvin.
Kelvin, thank you very much, okay? And this is going to be a negative slope, so you already know this equation. So this represents the slope, this is y equals mx plus b. So this A, which is your y-intercept, is what's known as the frequency factor. What the frequency factor tells you is how many of the collisions occur with the correct energy and orientation. So with some collisions and some reactions, imagine that you're going to have these oxygens collide. Well, these both have like small magnets on them. So if I just randomly throw these together, some of the times they're just going to bounce right off because the orientation just isn't right. But if they are lined up right, they're going to stick together. But if they're not lined up, they're going to bounce off of each other. So this is why just because you have a collision with atoms or molecules doesn't mean that necessarily the reaction is going to take place. The orientation has to be just right. The energy has to be just right. The energy has to be above that threshold, okay? So, now this is where this leads into another, looks like a random equation, but I'll explain where it comes from in just a second, okay? So don't flip out. Do not flip out.
I'm flipping.
You know,
I told you not to flip out.
No.
Imagine I just did a backflip right now.
Nope.
I'm gonna learn how to do backflip. Or
Don't flip out,
You
guys.
got me flipping.
Feels like a.
I don't want this.
Yeah.
I mean,
Kevin, can you do backflip? You look like you could.
Yeah.
Use the energy
maybe I
side.
haven't tried.
You can do it one hand curl. You should.
Try right now.
You
I
should
can't
try.
do
Go
that.
back there.
Well, if you can do it one hand, you can do a backflip and you can
Do it.
Sure, why not?
Dude,
Or
you
if
should have
not.
been a cheerleader. What were you doing?
Yes. You missed your calling.
It's never too late.
What was this football stuff? Could have been.
Exactly.
Could have been in your little
Pick up the
skirt and
pom-poms.
pom-poms, bro.
I can pick up the
My
pom-poms.
dad.
Last time I picked up the pom-poms, I dislocated my knees in debate class. That was
Yeah,
fun.
that makes that
Couldn't have ended well.
No, I ended on the floor crying.
Actually, she
Okay.
came in a wheelchair.
I did, I
We are
know.
Whoa.
Yeah.
What was this?
Freshman year.
Oh, okay.
Yeah.
Everybody has to have that. Okay, so, everybody does stupid things as freshmen. So, let me explain, this equation looks daunting, okay? It looks horrible. But all this is, if you think about it, is the slope-intercept form where you're finding points in between two values on a line. So all this is the natural log of K2 over K1. Those Ks are your reaction constants, okay? But they're temperature dependent. These are your temperatures in Kelvin, okay? So typically what would happen is that you're going to say, hey, a particular reaction at a temperature of 200 degrees has a K value of 10. We're going to raise the temperature to 300 degrees. What's going to be the new K value? Okay? So all this is if you think about this, these are just X and Y coordinate values where you have K, your natural logs of K as your Y values, and you have 1 over temperature as your X values. The E sub A over R is just the slope of the line. Okay? So this looks really, really weird. It's just literally, it's a slope-intercept form involving natural logs and 1 over temperature in Kelvin. Okay? That's all it is. This is just like y2 minus y1 equals x2 minus x1 multiplied by the slope. Okay? Now, here's where this has to be very specific in terms of units. This activation energy has to be in joules. Okay? Most of the time it's given in kilojoules. The reason that it has to be in joules is because of that gas law constant, which is 8.314 joules per mole Kelvin. So if you leave activation energy in kilojoules, it doesn't cancel out the joules that are down there in the R value. Okay? So here's how this problem would play out. You would be given 3 of the 4 variables. You'd be given like 2 of the K values and 1 of the temperatures, or both temperatures and 1 of the K values. Now, how do you undo natural log? Yeah, I'd have to keep that in mind. I'm just saying. Now, here's the one last random equation, and this is kind of rando, but just go with me here.
I'm sorry.
That was a big sigh. I think it was needed. What is that?
What is that?
What letters are those?
Frequency frequency.
I don't like this.
Oh, that's an F?
Fraction of
Do you like it when we read what you're writing as you write it?
molecules
Is that like something you really enjoy?
Oh, more than likely.
that
I can imagine. I think
When I retire, I'm just gonna start, I'm just gonna go up to random people on the street and go, I'm gonna start writing. Can you guys guess what I write? I'm gonna have like my own projection screen. And then have a little bowl like for donations, you know?
Are you also gonna be homeless?
Well, I don't know, I'm just saying.
It's up there.
My,
We'll see when we get there.
He invested.
I don't know.
that has
Based
an
upon the stock
energy
market, what it's doing
So
today.
true.
Amen.
All your money.
Happy Liberation
Greater
Day.
than.
greater than
Notice that he did it after the midterm
Activation
elections, or after the special elections
Uh-huh.
in Florida,
Well, why would he do it before
because he
that?
knew it was
could
gonna
affect
tank, and
things.
that's why he waited until afterwards.
This is crazy.
I know,
Politicians
shocking.
thinking about things? That's
Well, I
worse.
know. Okay, so let me explain what this is.
I say going in political science.
So what this number gives you is what's called the frequency. It's how many collisions occur above the threshold. Now, obviously, your R is going to be the same R that you've been dealing with. So what units does your activation energy have to be in? Joules. The temperature, Bethany, has to be in
Kelvin.
Kelvin. Okay? So if you go through the math, because it's negative E sub A, first off, this value has to be less than 1. Okay? Because it's a frequency. It's like a rate, it's like a percentage almost. If you do this and you get a value of like 50, you have done something horribly wrong. Okay? Typically, these are very small numbers. But think this through. As the temperature goes up, what should happen to the value of F? Because these are the collisions that are above the activation energy.
Go up.
Yeah, so as your temperature goes up, you should see that the frequency value gets bigger because you're going to have more collisions that are above the threshold. Okay, I'm done.
alright.
You're not, but I am.
All done, I go home.
Oh,
Yeah, that was-
Oh, Berg.
Sorry.
this is done and she goes, well, I am. You're not.
Because I did.
About to be.
That was so
Trying to go
uncalled
like down one.
I'm about to be done.
Uncalled.
Stage 50? What?
What's going on?
This will make sense.
It doesn't though.
See through
See, assume
zero order.
So he told me.
50
50.
We're
Starting with 50, that's so big.
Sorry.
That's because you've already done a lot.
What does it mean only 39 and 80?
Okay, you should have
I'm
done.
only doing 89, 39 and 80.
But I did it. Not with
I'm
my
reading
heart.
instructions wrong.
Not with my heart. You know, I need to get a 3
No.
on the AP Chem exam to
I'm
get
about
credit
done.
at the zoo.
If you're about
That does
done,
not
well,
look
it's
about-
gone for like
I
3
know.
hours.
Yeah.
There we go.
I'm stressed.
Wait,
One's is 39 and one's 80.
Okay, this will make sense when you get to question 50, okay? You're gonna have some data. It'll make sense when you read the question. Only do the values for 39 and 80. Don't do all of them, okay? It'll make sense. You have to draw a graph, okay? Shocking as that may be.
How many graphs do we have to draw?
2,
What page is it?
This can't be.
on page 615.
Is it like a pretend graph or like a
No, this is like, this is
Aw,
legit graph.
man.
These are not sketches.
graph?
No.
Like graph paper?
Graph paper graph.
No.
This is the worst day of my life.
Yes, there's 2 graphs. This is the worst day of your life. I
It's so
doubt that.
Joker.
I knew it. Oh, how about you the other day?
You're done after this. It's not when you're-
Yeah, he really doesn't get, I mean, anyway.
What is this? Is this 14-3?
I don't know.